Today on the deep dive, we're plunging into a surprising challenge facing a really fast-growing U.S. industry, industrial hemp. You might picture, green fields and good vibes, but there's this tiny, powerful villain at play: pollen grains. We're dissecting a fascinating new study that simulated how wind carries hemp pollen right across the entire U.S.
Yeah, and this isn't just academic curiosity. Cross-pollination between neighboring hemp fields, it's actually a massive problem. It can lead to contaminated seeds, it definitely reduces oil yields, and sometimes even forces farmers to destroy their entire crop.
Destroy the crop? Wow.
Absolutely. We're talking serious financial losses. Think anywhere from, say, $12,000 right up to millions. There was even one lawsuit in Oregon alleging over $8 million in damages.
$8 million.
That's
That's
cool.
just staggering. So understanding the study, it really becomes critical then, doesn't it? It's the first really big simulation of hemp pollen dispersal, and it immediately shows a key pattern. Pollen deposition rates, they generally ramp up from summer into autumn.
And what's really fascinating here is the huge day-night difference in how it spreads, what scientists call diurnal variation. Basically, nighttime conditions. They favor pollen dropping closer to the source, but daytime conditions let it spread much wider, though maybe less concentrated nearby.
So like a localized drop at night, but a longer journey during the day?
Exactly. Precisely. And here's the really wild part. Even a tiny fraction like 0.01% of the huge amount of pollen. And remember, a single male plant can release maybe 100 million grains.
100 million?
Yeah, even that tiny percentage can still cause effective cross-pollination far away. This shows that fat tail problem. Small amounts travel incredibly far and still do damage. It's like an invisible widespread threat.
Okay, let's unpack this a bit more. For a farmer actually out there on the ground, how do these day-night shifts and seasonal changes translate into, practical risks?
Well, it's a really stark difference. Within about 20 kilometers, maybe 12 miles or so, from the source field, nighttime depositions are dramatically higher.
How much higher?
Sometimes 10 to even 100 times greater than during the day. So, for instance, maybe 97% of the pollen drops within that range at night, compared to only about 81% during the day.
Okay, big difference close in.
But, and here's the twist, beyond that 20-kilometer mark, we see that fat tail effect kicking in again, particularly during the day. So, although less pollen might be falling overall nearby, the stuff that does get airborne travels much, much farther.
How much farther are we talking?
Well, the simulation went out to 50 kilometers, but the pattern suggests it goes beyond that. It lines up with older reports suggesting travel up to 200 kilometers, maybe 120 miles. It seems daytime updrafts create this kind of pollen shadowless deposition near the source, which actually lets more pollen escape and travel those really long distances.
Right, so if pollen is traveling that far, the old rules of thumb for isolation distances, they just don't cut it. What does this study suggest for actually assessing risk and finding, real solutions?
Yeah, exactly. The study introduces this novel idea, a vulnerability metric. It combines the calculated pollen dispersion area with county-level data on how much hemp is actually being grown. And using this, it identifies the regions most vulnerable. We're looking at places like the Upper Midwest, the Ohio Valley, and the Northeast.
Any specific states jump out?
Oh, yeah. States like Montana, South Dakota, Idaho, Wisconsin, and Kentucky showed particularly high vulnerability according to this metric.
That's incredibly specific. So given that current isolation distances, what are they? Typically 1 to 5 kilometers? Clearly aren't enough if pollen's traveling 20, 50, maybe even close to 100 kilometers. What strategies can farmers use?
Good question. The study offers several key recommendations. Things like voluntary pinning systems, basically online maps where growers log their field locations, planting times, and importantly, flowering dates.
Okay, so better information sharing.
Right. And also creating dynamic, sort of time-dependent risk maps. Imagine maps updated with real-time weather data showing current dispersal risks. And maybe fostering more community-level planning, where growers in an area actually coordinate planting times and varieties. There's even talk of potential for insurance models based on this kind of regional risk assessment.
That makes sense. So it really moves beyond simple rules to understanding complex atmospheric science for, better risk management. This deep dive really shows us that managing hemp cross-pollination isn't about one-size-fits-all rules at all. It's about getting to grips with these complex regional atmospheric dynamics.
Exactly. This study, it's pioneering in that sense. It provides a critical foundation for much more sophisticated agricultural risk management. And what's also quite interesting is that the methods they used, They could potentially be applied to tracking the dispersion of any lightweight particles, not just pollen. That has implications far beyond just hemp farming.
It certainly does, which makes you think, what other agricultural challenges or maybe even environmental issues could benefit from this kind of deep dive into how tiny particles travel? We'll leave you with that thought. Thank you for joining us for this deep dive into the surprisingly complex science of hemp pollen.